Hey folks, this is the first lesson in our unit on nuclear chemistry, and in particular we're going to be just sort of diving in with looking at nuclear decay in particular, so kind of the really heart of nuclear chemistry and nuclear reactions. So a couple goals for this lesson. First, talk about what nuclear decay is and what causes it to happen. And then second, look at the 5 different types of nuclear decay and identify what products are produced from those different types of decay and write balanced equations for each of those different types of nuclear decay. So let's get started. Now first, in order to be able to actually do this stuff, you need to remember some stuff about atomic structure and some notation that we use. So a few refresher questions for you. First, what is it that determines the identity of an element? What is it that all carbon atoms have in common or all sulfur atoms have in common, for example? So that's the first thing. Second, review isotope notation. So we have a special way of writing and representing different isotopes very quickly. So that's the second thing. And then third, how many neutrons are in an atom of sulfur-33? So I encourage you to pause for a moment and just see if you can figure out the answers to each of these things. If you need to go back through your notes, that is fine. Okay, hopefully you have some answers at this point. You paused if you needed to. First, what determines the identity of an element? Number of protons. That is it. All hydrogen atoms have 1 proton. It's the only thing that we are guaranteed that they all have in common. Different numbers of electrons on atoms of the same element are called ions. And having different numbers of neutrons and consequently different atomic masses, we call those different isotopes. But if we change the number of protons, that means we have totally changed the type of element that we've got. Okay, so that's the one thing that all atoms of one element have in common. Second, to represent different isotopes. Okay. We have a standard notation. We've got the symbol of the element written nice and big. And then what we have is 2 numbers written in the upper and lower left-hand corner. In the upper left-hand corner, we've got the mass, which if you recall is equal to the number of protons plus the number of neutrons. We can also find this by looking at the number that comes after the name. So when we say carbon-14, that means a carbon atom with a mass of 14, a combined number of protons and neutrons that's equal to 14. The reason we don't need to specify the atomic number is, if you recall, all carbon atoms have 6 protons. That doesn't change. So by saying carbon, we know it's got 6 protons based on the periodic table. And that number goes in the lower left-hand corner. So we've got mass in the upper left, atomic number, which is the same as number of protons, in the lower left. And then if we wanted to figure out the number of neutrons, then, since the mass is the protons plus the neutrons, and the atomic number is just the protons, we can just subtract those 2 to get the number of neutrons, which I guess means I just gave away the answer to number 3. So to figure out the number of neutrons in sulfur-33, we start with the mass of that particular isotope, which is 33. It's given to us in the name. And then we subtract the number of protons in an atom of sulfur, which we find by looking on the periodic table and looking at the atomic number. And when we subtract that, we determine that there are 17 neutrons in there. All right. So now we're ready to actually talk about some new stuff in nuclear radiation. Nuclear radiation, nuclear decay, radioactive decay, these are all terms really for the same process, which is that we've got an unstable atom with an unstable nucleus, and what it does is it kind of self-destructs a little bit. It takes some part of its nucleus and spits it out. Okay. And what that means then, since we're messing with the nucleus, that will often change our element into a different element. Because sometimes we're losing protons and like exchanging things around a little bit. So with nuclear reactions, what we find is we're actually changing the element. It's not like in previous chemical reactions where once we had an atom of carbon, that atom of carbon stayed. Now we've got weird situations where that carbon could turn into something else. Now, there are lots of different ways for the nucleus of an atom to self-destruct, which means that there are lots of different types of nuclear decay or nuclear radiation. Okay. The first one that we've got is an alpha particle, or alpha decay. So what a nucleus might do is it might spit out 2 protons and 2 neutrons. Okay, and that's it. And basically, if you've got 2 protons and 2 neutrons, what you have is a helium nucleus or a helium atom with a charge of +2. Either way is fine, either way that you want to look at it. So that's one thing that a nucleus can spit out. Another thing a nucleus can spit out is a beta particle. And a beta particle is just a fancy way of saying an electron. Okay, that's really all it is it's just an ordinary electron. I don't know why they give it a fancy name other than to sound smart. Now, to represent a beta particle, what we do is we use a little e or a beta, which is this funny little Greek letter right here. Either one's fine. Electrons, if you recall, are very small, so we say that the mass is essentially 0, and doesn't have any protons, but it's got a charge of -1. So in the place of atomic number, what we do is we actually put a -1 to represent the charge of -1 on a beta particle. So that's another thing that an atom can spit out of itself. A third thing that it can spit out is a gamma ray. Now, if you recall from a couple of units ago, a gamma ray is a very high energy electromagnetic wave. So in other words, what it's really doing is just spitting out energy. We can think of it that way. Now, the way that we represent a gamma ray in isotope notation is we have a gamma right here, which kind of looks like a weird Y, I guess you could think of it. And then this gamma ray, it has no protons, no neutrons, no electrons, no mass, no matter whatsoever. It's just energy. So the mass then is 0 in the upper left-hand corner, and the number of protons is 0 as well. Another thing that can be emitted by an atom when it goes through nuclear decay is something called a positron. And positrons are kind of like electrons, except if electrons were positive. Now, this is not the same thing as a proton, because we're still talking about something that's very itty-bitty, way smaller than a proton with a mass of essentially 0. So it's this weird new particle that we don't really encounter until we're looking at nuclear reactions. So to represent a positron, again, we use the E, mass of 0, but this time our charge in the lower left-hand corner is +1. Okay. Some other stuff that can be spit out, oh dear, this little line here needs to be over this guy. So these funny little V things represent neutrinos, and if there's a line over the top of it, antineutrinos. And those are just some other particles that have no mass, no charge, they just carry some energy with them. And it's not really entirely clear yet what neutrinos and antineutrinos do. We're still kind of playing with them and kind of what their purpose is. But currently, neutrinos and antineutrinos are mainly useful because we can detect them and get a sense of what kinds of radiation are going on. But neutrinos and antineutrinos in and of themselves don't really do a whole lot. They don't have a lot of mass, or they don't have any mass or any charge, so they're just sort of side players in this game. Okay. Some other things that can be spit out that we're not really going to worry too much about. An atom could spit out a proton, which is the same as an atom of hydrogen. Same thing. Could spit out a neutron, on the other hand, which is represented by an N. It's got a mass of 1, but no protons or electrons, so an atomic number of 0. And then other isotopes also end up getting spit out as a result of this. So I know that's a lot. We're going to look at each of these in detail separately. So don't worry, that was just an overview. Now, to compare the effects of some of these different types of radiation, we've got this little animation for you. So, excuse me. Hey, got it up. All right. At the top here, we have an alpha particle, which is, if you recall, the same thing as a helium nucleus, or a helium isotope with a charge of +2. Okay. And then in the middle here, we've got a beta particle, which, if you recall, is just an electron. And at the bottom, we've got a gamma ray, which, if you recall, is just energy. Okay. Now, what we see is the different layers that each of these radiations, each of these particles can penetrate through. If you notice, alpha particles, not really that scary, because all you need is like a piece of paper. And something even that thin will stop alpha particles in their tracks. They're very easily deterred. Beta particles, on the other hand, are a little bit smaller, so they're able to get through a little bit more stuff. But basically, once you've got like a couple inches of like aluminum or something like that, they'll pretty much be stymied as well. They also tend to die off within a few feet of their source, just because they'll get captured by something else along the way. So beta particles, also not that scary. Gamma rays, on the other hand, go easily straight through all those things, straight through a lot of things. They will go right through wood and right through brick. Basically, we have to have like a good solid amount of lead before gamma rays are actually stopped. So gamma rays are the ones that can actually penetrate a lot of different materials, which makes them a little bit scary. Okay. Now, the reason that gamma rays are so able to penetrate through things is because they don't have any charge, they don't have any mass, they're just energy. So there's not really a lot of stuff that can block them very easily. So they can travel through all sorts of things. Again, they're the highest energy on our electromagnetic spectrum. And if you recall, this was the cause of so many health issues after the atomic bombs at Hiroshima and Nagasaki during World War II, or at the end of World War II, is that after the atomic bomb detonated, there was a lot of gamma radiation that was being released as a result of that nuclear reaction, and that gamma radiation messes with you. So people got very, very sick as a result of it, and they weren't even safe by like staying in their houses, because gamma rays will go right through them. So pretty scary stuff. Okay. Now, the reason for this to happen is basically we've got this like fight of two different forces within every atom, battling it out to see who will win. Okay. Now, the first force that we've got is the strong nuclear force. And we don't know a ton about this, but we know that basically what it does is it holds our protons and neutrons together. It's like the super glue that holds us together, the nucleus of an atom. But at the same time, if we recall basic electrostatic information, like charges repel. So what happens also is our protons that are also tightly packed into a nucleus are also trying to push apart from each other. So this electrostatic repulsion is pushing them apart, strong nuclear force is pushing them together. Okay. Now, mostly, fortunately for us, the strong nuclear force wins, and we get our nuclei actually, staying together. But every now and then, something will happen that will cause that electrostatic repulsion to win out over the strong nuclear force, and that causes our nucleus to break apart, okay, which is called radiation. Okay. Now, it turns out that this process is very common with heavy atoms, anything that has an atomic number over 84. And then there are some lighter isotopes of other atoms that are similarly unstable, where we've got not a really good balance between that electrostatic force and that strong nuclear force. And then what happens is that electrostatic force wins out, and we get this nuclear decay and something called transmutation, which basically just means that atom then decomposes and turns into a different element. Okay. Now, we can represent this process using a radioactive decay equation, or an equation to describe a nuclear reaction. And what we do is we use isotope notation in these to keep track of changes in mass and atomic number. But what's really important to remember about all of these equations is that the charge and the mass have to be conserved. We can't go creating or destroying charge or mass. Even when we're messing with the nuclei of different atoms, those things have to be conserved from the left side of the equation to the right side of the equation. Okay, so to compare chemical and nuclear reactions really quickly. Right? Chemical reactions, we're just talking about exchanging electrons. Electrons are the only things that really do anything in chemical reactions. Our nuclei just kind of sit there and don't do a whole lot. Whereas in nuclear reactions, we actually start getting those protons and neutrons involved. We start messing with the nucleus of our atoms. Okay. Second main difference is that if you recall, we had exothermic and endothermic chemical reactions. We could release or absorb some amount of energy, but in nuclear reactions, way more energy that's being released as a result of these reactions, which is why, you know, atom bombs and hydrogen bombs and stuff like that are kind of a big deal. They release a lot of energy. Okay. So let's start looking at each of those 5 different types of nuclear decay now. And what we can do is keep watching to see that charge and mass are always going to be conserved. Right? Here's the first nuclear reaction to consider is electron capture. And basically what happens here is we have an electron that's orbiting around the atom, and for whatever reason it gets sucked into the nucleus. And what's kind of interesting is that when that electron meets up with a proton, they can actually form a neutron. Okay? So proton plus electron equals neutron. And then also a neutrino is produced, but we're not really as worried about that. So we see this in this reaction here. Proton plus electron gives us a neutron and an antineutrino, or and just a neutrino, excuse me. Okay. Now, this causes this transmutation to occur, and this is just an example here, where we've got mercury 200, it captures an electron, and it transmutates into gold 200. Okay. Now, key idea for this type of equation is that our atomic number is going to decrease by 1 because we've taken one of our protons and turned it into a neutron with the addition of an electron. Okay. But the mass number stays the same. Okay. Now, if you look here, what's kind of nice is we can check our work by checking to make sure our top numbers are conserved on both sides and our bottom numbers are conserved on both sides. So on the left side here, in the upper left-hand corner, we've got 200 plus 0. That's a total mass of 200. On the right-hand side, still 200. So our mass has been conserved. We're in good shape. Okay. Then we compare for our lower left-hand numbers. Everything on the left side of this equation. We've got 80 and -1. If we add those up, that's a total of 79 for our atomic number on the left-hand side of this equation. And on the right side, lo and behold, also 79. So we have conserved mass and charge through this process by keeping the mass the same and decreasing the atomic number of our starting element by 1. Okay, so just an opportunity for some practice to look at electron capture and practice writing equations for argon 37 and iron 55. So I encourage you pause the video, try to write these, and then compare your answers to mine. Okay, here are the correct answers. So for argon 37, again, isotope notation, we've got mass of 37, atomic number of 18 by looking at the periodic table. That gains an electron, and what we are produced with then is a new element with the same mass, but an atomic number that is decreased by 1, and if we decrease the atomic number of argon by 1, we are left with chlorine. And a neutrino is produced. Okay. For iron 55, same deal, we've got iron, mass of 55, atomic number 26, gain an electron, and we end up with manganese 55 as a result of that. Again, we can always check our work by comparing our upper numbers on the left side of the equation versus the right side of the equation, and the lower numbers on the left side versus the right side to make sure that those always stay the same. Next type of nuclear decay is beta decay. Okay, and this is sort of electron capture in reverse, basically. So what happens here is instead of adding together a proton and an electron to form a neutron, instead we have a neutron that turns back into a proton and an electron, or a beta particle. And this electron or beta particle just gets shot out of the atom, basically. So what happens here is, again, our mass stays the same because we're only exchanging electrons which don't really have much in the way of mass. However, our atomic number increases by 1 because we took one of our neutrons and turned it into a proton and an electron. So what we see here then is that our, again, our mass number stayed the same from one element to the other, but our atomic number increased by 1. And again, we can do the same thing here where we see on the left side of the equation we've got 90 for our atomic number, and on the right side we've got -1 and 91, which if we add them together is 90, same that we started with. So some examples for you to try out. Pause the video, see if you can do these. Okay, first one, carbon 14. Again, isotope notation, mass of 14, number of protons or atomic number is 6. What happens is we spit out a beta particle, atomic number increases by 1. So we turn from carbon 14 into nitrogen 14 with an electron spat out as well as an antineutrino that we're not too worried about. Now what's kind of cool about carbon 14 is this is how we're able to keep track of how long like fossils have been in existence, for example, because carbon's in like everything, and a small amount of that carbon will be carbon 14. So if we can keep track of how much of that carbon 14 has decayed into nitrogen 14, we can actually tell how long that particular substance has been in existence just by looking at how much of these reactions have already occurred. Kind of interesting. Okay. Second example, potassium 40. Okay. Here's our isotope notation for potassium 40, atomic number of 19. When we release an electron, we have turned a neutron into a proton, and so our atomic number increases by 1 to give us calcium 40. And again, we can always check to make sure that our upper numbers are the same on both sides of the equation, and that our lower numbers add up to be the same on both sides of the equation. Third type of nuclear decay is positron emission. Now this is very similar to beta decay, except instead of releasing an electron, what we're doing is releasing a positron, which again is like an electron, but with a positive charge instead of a negative charge. Now what happens here is that our mass number again stays the same, but our number of protons decreases by 1 because we've had a proton that turns into a neutron and a positron. So as a result, our atomic number decreases by 1. So if we see here, we started out with sodium 22, it's going to decay into neon 22 because we have turned one of those protons into a neutron and a positron. Some examples for you to try out. Pause the video. We've got carbon 11 and potassium 38. Alright folks, by the way, first of all, this says position emission. It should be positron emission. Haha. Alright, so carbon 11, when it emits a positron, again, what we see is that that atomic number decreases by 1. So we go from being carbon 11 to boron 11 with an extra positron, or, you know, positive electron basically being emitted as well, along with a neutrino. For potassium 38, again, same deal. We've got potassium with a charge of 38. It loses one of its protons, turns it into a neutron and a positron, and that gives us argon 38 instead. And again, as always, we can check our work by making sure that our top numbers add up to be the same on both sides, and our bottom numbers add up to be the same on both sides. All right. Fourth type of nuclear decay is alpha decay. All right, now again, alpha particles are those helium nuclei. So with alpha decay, what we're doing is we're spitting out 2 protons and 2 neutrons. Now as a result of that, what happens is our atomic number decreases by 2 because we lost 2 protons, and our mass number decreases by 4 because we lost 2 protons and 2 neutrons for a total of 4 things in our nucleus. So an example here, we've got uranium-238, okay? When it releases this alpha particle, which is shown on the far right here, we know it's going to lose 4 from its mass and lose 2 from its atomic number, which gives us this, right? Again, as before, we can check our upper number, 238, on the left-hand side. On the right-hand side, 234 plus 4 is 238. It's the same. And then for our lower number, our atomic number, we've got 92 on the left, and then 90 plus 2 is 92 on the right. So we're good to go. All right. Try this out. We've got americium-241 and polonium-212. Pause the video, give it a shot. All right, americium-241. Okay, so americium has an atomic number of 95, so we've got americium-241. Our atomic number decreases by 2, our mass decreases by 4, and we also have an alpha particle. Now again, an alpha particle can be represented by He, because it's really a helium nucleus, or we can represent it with an alpha. Either one is totally fine. Okay. And then, for polonium-212, same deal, we've released a helium nucleus, our mass drops by 4, our atomic number drops by 2. We look on the periodic table to see what is it that has 82 protons, and that turns out to be... Fun fact about alpha decay, it keeps you alive at night. Alright, because americium-241 and its alpha decay is actually used in your smoke detector. There's a very small amount of americium-241. You have no risk of any sort of dangerous radiation because remember, alpha particles are stopped by like a piece of paper. So I guarantee your smoke detector case will protect you from those alpha particles. This decay occurs over a really long period of time, so the rate of radiation is really slow. But this ends up being useful because what happens is those alpha particles that get emitted by our americium-241 run into the atoms in the air and create positively charged ions. And then our smoke detector kind of counts to see like, okay, how many positively charged ions do we have in here? And if it's just air that our alpha particles are running into, that number is very consistent. But as soon as we have smoke entering the case, then it becomes very different, and our alpha particles interact differently with smoke than it does with ordinary air. And that change in the number of positively charged ions triggers an alert for the smoke detector, and it beeps, and everything's all great, and your life is saved. That's great. All right, last type of nuclear decay, gamma radiation. Now, gamma radiation very rarely occurs by itself. It's usually tagging along with another type of radiation. Now again, gamma rays have no mass and no charge, so as a result, they don't really do anything to change the equation. They can kind of just get tacked on at the end without having to worry about whether the equation gets balanced in terms of mass or charge. So those just get tacked on there, which makes them sound like throwaway, but again, gamma radiation is the kind that kills you, so not really a laughing matter. Okay. So just to review, we've got 5 different types of nuclear reactions to consider: electron capture, beta decay, positron emission, alpha decay, gamma radiation. This slide is here just to kind of summarize everything and be a quick reference tool for you. That is all I have for you. Have a wonderful day.